Hi. Okay, so today we're going to be looking at the chi-squared goodness of fit, and we have already looked at doing a dihybrid cross. So we're crossing um, individuals, but we're tracking, in this case, two genes. And when we did our dihybrid crosses, those two genes might be on the same chromosome, or they might be on two different chromosomes. If the genes are found on the same chromosome, we consider them to be linked. And if they're on different chromosomes, they shouldn't be linked, and you should get normal Mendelian ratios. If the genes are on the same chromosome and they're linked, we might not be getting as many recombinants as you would normally see. All right, so in doing this example, I think it'll be important that you go to our Google Drive folder and find that chi-squared examples document. We've already looked through this document in the past, so here's what it looks like. We did it for an ecology example, and we're going to scroll all the way down to the last page, and it goes over a genetics example. The first page, you might need to scroll back up if you want to see the critical values table, but in general, everything I'm going to be going through should be within here. And I'm not sure if my numbering is quite right because it looks like it's a little funky here. I'm going to change this for you. Hopefully it's right later. And that should match the numbering, hopefully, on the screen as we move through. Okay, so let's go over to our goodness of fit. So with our goodness of fit, this is our normal. We're going to use the same chi-squared equation, and we're going to be comparing our observed and our expected frequencies, just like we were before. But last time in ecology, we were seeing if they happen independently or not. So this is the goodness of fit model. And the difference between that and the way we did it before is how we calculate those expected frequencies and how we determine our degrees of freedom. So this is actually different from the way we did it in ecology. But the things that are similar is if our p-value is less than 0.05, we will reject our null. If our chi-square value is greater than the critical value at the probability of 0.05, then we can also reject the null. So in genetics, we can use the chi-squared goodness of fit for monohybrid crosses. You could maybe cross two heterozygotes and see is the dominant phenotype happening at a three-quarters of the time, and the recessive trait phenotype happening only 1/4 of the time. Why might that be happening? Well, maybe there's an environmental thing that could be excluding one of those phenotypes. But the way we're going to apply it today is we're going to be doing dihybrid crosses and looking at some observed phenotypes, and we're going to see if that phenotypic ratio matches the expected ratio. If it doesn't, it's possible that those two genes are linked. Okay, so again, genes are linked if they're found on the same chromosome. All right, so this example, we're going to use fruit flies. And the same example that we did in the last one, except we're going to be looking at the ratios and not kind of going through the whole crosses. But here's our wild type fly. And our wild type fly has a gray body and normal wings. And we're going to cross that with a mutant fly. So that's black body and vestigial wings. So our fly here is heterozygous for both traits. That's that F1 individual that we had done in our last example. And of course, this is a homozygous recessive for both traits. And here's what our observed offspring were. So there was 200 babies. Let's see if I can make this, if I can end up showing that to you. Down here on your chart, it should say 200. So there was 200 babies total. And we've got 64 that were gray and normal, 60 that were black and vestigial. And then here's our recombinants. And notice the number of recombinants is less than the number of non-recombinants. So that could be an indicator, is this gene linked or not because there's fewer recombinants? Or is it just that we got those numbers out of chance? And that's what the statistics are going to tell us. Did this happen just by fair chance, or was it too far away from chance to be considered following the Mendelian ratios? Okay, so the first thing that we need to do is we need to determine the expected frequencies. So we would go back and do a dihybrid cross that would show it not being linked. So we're crossing a double heterozygote with a homozygous recessive, and we know that that would give us a 1 to 1 to 1 to 1 to ratio. And so we're going to use that information to determine what our expected values are. And the way we're going to figure out our expected values for each of those phenotypes would be, you would take this ratio, so we know this is 1 out of 4 or 0.25, and then multiply that by the total. So there was 200 babies, so we're going to, for the gray and normal, we would take the probability of it being gray and normal, 0.25, and multiply that by 200, and that would give us 50. So really, it makes logical sense. If we had 200 flies, and we know the ratio is supposed to be 1 to 1 to 1 to 1, that we should get 50 of each. So 50, 50, 50, 50. And that's why when we look at this, our expected ratios are this, and that should also add up to 200. So here's our observed, here's our expected, and now we need to go through and actually calculate our chi-squared statistics. So we have our phenotype, our observed, our expected, and then when we do our stats here, here's our example just for the gray and normal. We're going to take 64 minus 50, so you can see that there, and we're going to square it. Then we're going to divide it by the expected, which is 50, and that gives us 3.9. So here's our 3.9. Oops, sorry. There's our 3.9. You're going to do that 3 more times. So 60 minus 50 squared divided by 50, and that's going to give us 2. 40 minus 50 squared divided by 50 is 2. And then 36 minus 50, square that, divide it by 50, and you get 3.9. So here's all of our values together. Then when we have all of our observed minus expected squared divided by expected, then we add it up and we get our chi-square value, okay? So this is that big chi-square value that's so important for us. Okay, so now we're going to take that chi-square value and we're going to be looking at our probability table and to be able to determine if we're going to accept or reject the null. So one thing we could take that chi-square value to determine what the p-value is, and we could also use that chi-square value and compare it to a critical value, which are these things down here are the critical values, and determine if we accept or reject if it is less than, or if it's greater than the critical value at 0.05. So, but to be able to use this chart, we need to know our degrees of freedom. And of course, this is where the level of probabilities fall. And this 0.05 is kind of the cutoff. So we need our critical value to fall somewhere over here. So to determine the degrees of freedom, for this example, well, actually for any of them, you take the number of genotypes and you subtract it from 1. Okay, so the number of phenotypes. The number of phenotypes minus 1. So we have 4 different phenotypes. And since we have 4 different phenotypes, we subtract 1 from that, and we have degrees of freedom of 3. Okay, if we only had 2 different phenotypes, then we would do 2 minus 1. But in this case, we have 4 phenotypes minus 1. All right, so now we know our degrees of freedom is 3. So with that, we're going to look for the p-value and compare that to our critical value. So our chi-square value was 11 point, let me go back and look at that. Our chi-square value was 11.82. So now we're going to look over here and see, where does that fall in? We have 11.82 should fall between 0.01 and 0.05. Okay, so it falls in between the 11.34, this keeps popping up, keeps falling in between those two. So that's going to be important. So we know that with 3 degrees of freedom, our critical value falls between 11.34 and 12.84. So our probability is 0.01. And because of that, we know that 0.01 is less than 0.05. so we can reject. There's another way we can do this, is that we can take our chi-square value and compare it to the critical value at 0.05. So the critical value at 0.05 is that 7.81. So we know that 11.8 is bigger than 0.05. Because it's bigger, then we can reject. Okay, so 11.82 is greater than 7.81, so we can reject the null. Okay, in either way. So that's how you go through and do it. There's quite a few more examples provided for you, with the assignment, and also in the Google Drive folder. So make sure you take a look at those. All right.